Continuing down the volume and surface area path to three-dimensional geometry, we have now pyramids and cones. Pyramids and cones are like pointy things rather than sort of the blocky kind of objects we had with prisms and cylinders. Pyramids and cones, as you probably know, are things that rise to a vertex rather than just going straight up. So there's just one base, and then all the corners come in and produce an edge, and those things go up to the top like that. So that's what they look like. Here's your questions for the... I can make that bigger. Oh, a little bit. There's your questions for the video due now when you first come to class. There's all of them there, better for you. Okay. All right, back to what the notes are about. Oh, can I move this up just a little bit? Are you sick of me talking to myself? Okay. Right, so this section's about how to define the surface area and volume of pyramids and cones. Actually, like last time, 12.2 is about pyramids and 12.3 is about cones. 12.3 is about cones and cylinders, which is kind of silly. I think cones have more to do with pyramids and cylinders have more to do with prisms. So anyway, here's all the terms. The way the book defines them is kind of in paragraph form too, and they just kind of highlight them as they come up naturally in conversation. I'm going to use them so much you're not going to be able to forget what they are. We're really not going to spend a lot of time talking about oblique ones. I talked about them at the end of the last video about the prisms and stuff, but they're so annoying the book just doesn't want to touch them. I don't really want to either. They're just you need to know they exist, but I don't think you're going to ever see those much in any other class either. So fine. Just realize that you can't use some of the same formulas if they're oblique. I'm not going to. I don't think. Ooh, I'm not making a test this time. I don't plan on throwing any oblique. If I were making it, I wouldn't throw any oblique ones at you. That would just be even meaner than tying a cow to a barn. Okay. So let's get on with it. How do you find the surface area and stuff of these figures? Well, first of all, they're much harder to draw than what you're used to. Let's do the square pyramid, because that's probably the one that you're used to imagining. If you've been to Egypt, apparently this would be the one you'd think of. All right, so we have a pyramid like this. These things are called these edges coming straight up and down. These are the lateral edges. I'm worried about finding lateral area right now. The lateral area is all of these things added up. That triangle there. You know what? I'll make the triangle different colors. There's a triangle kind of on this side over here. There's a triangle in the front that would kind of obliterate that yellow one because it would go all the way across it. Oh, it makes a different color. Oh, cool. You can kind of see through it. And there'd be one in the back. The back one would kind of go like this. Yeah, you can kind of see all these different colors as they overlap. Ooh, pretty. Okay, so I have a back one, a left one, a right one, and a front one. Great. All of those kind of looks like watercolors with that. I'm just so impressed with myself. And there's also this square on the base. Now the square on the base is not part of lateral area. The lateral area in this case is actually for triangles. So let's think about what those triangles look like. Those triangles, if you were to lay them out this way, they would kind of look like teeth. If I was going to unwrap them and unzip the whole pyramid, I'd get these 4 triangles. Each one of these is the side of the square. Each one of these triangles is identical, because I said I had a square pyramid. So they're all these isosceles triangles, and each one of those isosceles triangles have the same height. So let's actually make up some numbers here. It's going to be a little bit easier if I do that. Let's call this a side of 8. And that's a square, right? So there you go. And let's say you would also have to know what the height of the... Well, actually, no, I wouldn't. Wait a minute. If I draw this, warning, is that involved in the area of these triangles? No, that's not the height of the triangle. Straight down the center of the pyramid. This height that I just drew right here, this is a very important little statistic here. Very important measurement. I want to make it a different color. It's so important. This little purple height right here. If I drew that on the pyramid, it's actually down the slope of the pyramid. If you were going to ski down this pyramid and you wanted to go the straightest, shortest path to the bottom, it would be that right there. There's one of those there. There's one of those down the front slope down here to this midpoint of this edge. There's one across here from the back up or the side up and from the back here. That little thing is very important. That is called, this thing in purple, this is called the slant height. And it is altogether different. It is longer than this pole holding up the tent here in the middle. That one, I just can't use all my colors fast enough. This one is called like the regular height, or the height. I call that the height sometimes. I think I'm the only one who calls it that. The regular, the actual height of the pyramid, that's used for other things. Slant height is what I care about if I'm using surface area. Okay, so let's say I just happen to know the slant height of this thing. Let's say I knew the slant height here happened to be, if that's 8, this is probably longer, so let's say that's, I don't know, 12. The area of this whole, all these triangles added up together, would be 4 times the area of a triangle, which is half times base times height, and that would be how I would do that. In general, when you have any old pyramid, well, let me draw a different one here. Let's draw a hexagonal pyramid. That'll be fun. Caught my hand on the screen there. It's really hard to draw straight lines at all on this thing, just because my hand catches the edge. Okay. Say we have a hexagonal base down here. Can you see my hexagonal base? So there's an edge like right there, and there's an edge like right here, and there's 6 faces, 6 triangles to this pyramid. And I like this to be my slant height color. This is really nice, don't you think? From the edge all the way down to the side, or like straight down the front here, going right to that one. I guess I could have made that one a solid line too, because you can actually see it. All right, so this one is called slant height. Check out my pretty L. Slant height. You're going, what's with that L, Mr. Craig? What the L is going on with that thing? L is, I need a T in there. The variable they use for that is L. I don't know why. Maybe because there's an L sort of near the front of slant, and S looks like a 5. Well, L looks like a 1 if you're not careful too. I don't know why they didn't call it T or something. But anyway, they call it L for slant height. And back to this, if you notice, we had 4 of these little things, and each one of these was 8. If you took out the 4 times 8 out of this piece, you'd notice if you took out just that piece, that 4 times 8, that 32, that little part right there is also known as the perimeter of the base. It is 4 times 8 that way. So we're just gonna use that here too. Let's say this stuff all added up. Perimeter of base, great. Perimeter of the base is P, all that stuff added up. Then, here you go, lateral area, right for the formula, drum roll please, is a half, because it comes from the area of adding up a bunch of triangles, and a half is just inherent in that. Perimeter of the base times the slant height. That's it. It's almost as nice as the lateral area of a prism in terms of trying to internalize that. But there you go. It is the same thing if you have a cone, kids. Cones are just like pyramids with a whole bunch of sides, and the sides are really tiny. But it works out the same way. You can call this thing the slant height. You can figure out the perimeter as, oh, I like blue for that, didn't I? You can find out the perimeter of the base. We used to call that circumference. You can also call it perimeter. But for all this, you can still say lateral area equals half PL. It's just here we kind of know that P is always going to equal the circumference of the circle. Some books actually say that since P is actually 2 pi r, if you substitute that in and you just knew radius, you could go straight to saying this. LA equals half times 2 pi RL, but you know what? The half and the 2, that's just 1. This is always going to be pi RL. Isn't that cute? This is sort of an alternate formula. Warning, alternate formula. We had alternate formulas for things like area of rhombus and, what was the other one? Oh, sector area. There might have been another one in last chapter. These are kind of nice to have around. It's not required. What's nice about this is you got one formula for cones and pyramids. What's nice about this is if you know pi and radius, you're ready to go on this. You don't have to worry about trying to find the circumference because you're just going to kind of mush it into this anyway. You can go straight from pi RL to figuring that. Okay, on to volume. Should I just go back? I drew all these nice pyramids. You want to really see me draw a bunch more? Oh, and there's this really pretty one here. It looks like it was painted by none other than Bob Ross. Okay, volume. Same thing, same shape here. The volume of this thing is a bit of a pain because I was given the base edge and I was given the slant height. For volume, and this is one of those formulas, they just say, here you go, apply it, don't ask any questions, just shut up and calculate. I hate that when they do that. They don't prove why this is. 1/3 times base times height. Really what that's like saying is, well, you know what, you've seen this volume equals base times height before, and of course capital B is area of the base. So here it'd be like 64 times this kind of height. When I say height here, I mean this height. So we needed that pink height here for something. We need it for volume. We don't need it for surface area. Volume, if this were just talking about base times height, we'd be talking about, I don't know if you can imagine this, it'd be like talking about a solid prism that's kind of caging around this pyramid. It would have the same height and the same base, so it would kind of like it's like the prism that this pyramid is occupying, where this point is actually on this square top. It turns out that the pyramid inside that box is exactly 1/3 the volume of the box. Now, why that's exactly 1/3 is not something that the book tells you. Like I said, they just kind of say, don't ask questions, just do it. It is a very complicated proof why it turns out to be this. Really, I can't prove this to you without using calculus, and the book says exactly this. The book has the same excuse, and they don't prove it. There's a really nice 3D model of that, though, but it only works for what do you call these, triangular prisms. There's a way you can actually take a triangular prism, and there's a template somewhere you can make this out of paper, and you chop it up, and you make cuts from like this bottom base. You cut it all the way up to this top thing here, and you kind of cut out this pyramid like this, and then you cut out from the top base. You cut out another pyramid that kind of goes to one of the bottom corners like that. You chop up that one, and then you're left with these three shapes. You can prove that the three shapes have the same volume, and if they have the same volume, and you can lean pyramids over and they have the same volume, then you kind of you actually see the three pyramids. But you have to kind of have that in 3D and lay it on a table and see how they stack up and that kind of stuff to see how that works. That would make there's actually a third pyramid there. It's really hard to describe, but you can say it. You can prove it has the same base and the same height as the other two. So it's very cool. But we're not going to do that. So back to this. I couldn't do this without the height, but you notice I could find this height. If I know this is 12, and I know this is 8, I don't know if you can still see what's going on here anymore. If that was 8, I could actually figure this out. There's a lot of this going on in this part of the book. Okay, I have here point A to point B to point C. I have a right triangle right there. It's kind of floating inside the pyramid, and this is a very common trick. This is like cutting chords in half to find sector angles. This is really popular. This from A to B, well, that's kind of like the apothem of this square. It goes from the middle to the midpoint of the side, and in a square that's going to be half the length of the side. So I know that has to be 4. And I am looking for this. I don't know the height of the pyramid, but I told you slant height earlier was 12. So you could use Pythagorean theorem to figure that out, and then you could find out the area. Sorry, I mean volume. But anyway, yeah, you can figure this out. It turns out that that height would be 8 square root 2. So this volume, just so you can see it here, is 1/3 times the area of the base, which is 8 times 8, times the height of the pyramid, which is 8 square root 2. Same thing happens for cones. Let's go back and put some. If I knew the area of that hexagon, I could find the volume. 1/3 times area of the base. Notice I'm writing that. Times height. So same thing. If I knew L and R, this is R of course of the base, you can always find H. This will always make a right triangle in a cone, which is kind of nice. You don't have that difference between slant height and edge length or anything weird like that on the cone. So you know H and R and L always make a Pythagorean triangle, and you can figure that out that way. Yeah, the problems they don't seem like they're going to be that tough, but we've got more than 2 variables in a lot of these equations now, because they give you volume and height and ask for radius, or they give you volume and height and ask for surface area. It gets to be a little dicey. Oh, one last thing. If you have to find the entire surface area, back to surface area, you have to find the entire surface area of one of these things, realize it would be the lateral area plus the base. So here would be plus the circle. Or in that pyramid I had, would be the 4 triangles plus the square. So you're only adding on one base, whereas in prisms we're adding on 2 bases, because these pointy things only have 1 base. And that's about it. I could talk to you about what the shape of this thing looks like, but it's just so much cooler in class. But here's a quick preview. Whoa, there it is. Yeah, and you can spin this around in 3D. It's very cool. Kind of looks like this shape. I'm about to run out of time, but you know, I dare you to look away from this right now. This is the coolest thing ever, isn't it? Okay, and you can close it up, and that's a cone. I'll give you this link at school. Oh yeah, you can even do that when it's not completely closed up. All right, see you in class. Bye, kids.